surrogate model implementation of controllization functional on unitary with and without fraction query. So there are lots of undefined words which I will try to define in the next slide. Before that, let me introduce my collaborators. So they are Shojin Nakayama and Miyamura, both from University of Tokyo. And you can find them at this conference. Anyway, so there you go. So these four keywords: so circuit model, functional, controllization, and fraction query. So by circuit model, I mean a paradigm of quantum computation that uses quantum gates, measurements, and ancillars. And also, I should have included this discarding of ancillars if necessary. So basically, I'm pretty sure most of the audience here knows what this is, but I included here just to remind you that this is, so if you stick to circuit model and design your program based on circuit model, it's almost directly implementable by actual computer. So this gives you a low-level language for quantum computation. Now, next for functional. So by functional, I mean, of course, it's a function on a function. And here I specifically need to be functions on gates. So because gates are functions on quantum state, therefore it classifies as a function. And I want to design a functional of these quantum gates. And I'm specifically interested in how you can implement these functionals using in the circuit model. So I want to see whether we can convert functionals into a sequence of quantum gates which can be implemented directly. And this is one particular example. And so I'll come back to this later. Now next, controllization. So controllization is a process of making a controlled unitary when you're given a particular quantum gate. Okay, so first, what is controlled unitary? Just to sort of refresh your memory. Controlled unitary is a gate which is activated or deactivated by different qubits. So here, so in this case, if the control qubit is in the zero state, the unitary is deactivated, and then it gives you this. So the input in the target system is actually preserved. While on the other hand, if the state in the first case is 1, then the gate is activated, and phi is converted to u phi, where u is actually the input gate. But here I just want you to remember that you don't want to measure the first gate because that destroys the superposition of the control gate. So you want to do this coherent manner. And again, so now controllization refers to the functional that gives you control unitary. So I want this blue part in the middle to be given by this functional implementation. Finally, fraction query. So fraction query is so fraction query of a unitary is a unitary such that if you apply them sequentially many times, it gives you back the original unitary. Here is just one example of such unitary. So it's a half query, and it's half. So if you multiply them twice, it gives you back the original unitary. Now this is motivated by when you consider, for example, quantum simulations. So in one of the most well-studied forms of quantum simulation, you have so these unitaries actually are some kind of evolution operator for some particular quantum system. Like, for example, so U is given by as exponential minus IHP, where H is Hamiltonian or system that you can implement. And usually in these quantum simulations, what you do is you implement small increments of time, then you implement each increment individually. So in that case, it's natural except that you can actually you can choose the fractional queries because it just refers to you're just referring to this for each increment. Okay. Now, next. Now, before going on to our results, let me give you some background research on this. First of all, controllization is not that simple. First, when I started this research, we thought that by using Frederick gate, this controllization is quite trivial. So what is Frederick gate? So Frederick gate is a control swap operation. So if the control kit is in the zero state, input is actually preserved. But if it's in one state, then it swaps the state of the two qubits, basically. Now, if you use this, then, for example, maybe you might construct a function like this. But the problem is that, okay, well, let's go one step at a time. So if it's in a zero state, this phi does not swap. It just goes through without touching the input unitary. But since you have to create some ancilla, then ancilla goes to the unitary, the input gate, and it gives ancilla in this U0 state. Now, on the other hand, if the control qubit is in a one state, then the phi, the target system goes to the unitary, and then comes back to the original system. Now, in this case, the ancilla does not go through the unitary, and it stays the same. But the problem is that if you just look at the first two qubits, then it looks as if this implements the controllization function, but the ancilla is not factored out. So by measuring, for example, this ancilla state, you can detect whether the control qubit is in zero state or one state. And this shows that the first two qubits are not factored out from the ancilla, and this is not what we want. Of course, one obvious solution is to find some state which I named it 2, such that it's invariant under unitary. So if you change this ancilla state 2, then even though U is applied on 2, we chose 2 so that it's invariant, so we return the same state. But this requires that we know what U is in advance somehow, right? We have to know that there is some invariant state. Okay? So, but then we restrict the input. Right? We require that we know something about input. This is not what we exactly want for our controllization. Okay, so sorry, let me go back one slide again. There we go. Again, so this failed maybe because we chose some particular implementation, namely the Frederick gate here, right? But can we achieve what we want if actually go beyond this Frederick gate implementation? Well, the answer is actually no. This has been actually discovered by Araujo, and it was discovered independently, but the paper is published by Araujo in 2013. You can find it on the archive. So what they did was they considered this kind of arbitrary function that you can think of in using a unitary. And they asked whether you can use this kind of quantum network to implement this circuit, this unitary. But I remind you that this naive controllization is not possible from the outset, because over here on the left, this U, so U is in, so physical constants of U is independent of the global phase, right? So you can have extra global phase, but it shouldn't affect the overall evolution of the whole system. But here, the global phase becomes a relative phase, which can be detected. So we know this implementation, without this any adjustment, cannot be implemented. But so what they considered in this paper is that they added extra unitary to compensate for the global phase. But then even then, this is not possible. Okay, so how much in 5 minutes? Okay, thank you. So I'll try to be quick about it. So then, what we did was we actually found a way to implement this controllization circuit without, if we can use fraction queries. And this is the exact circuit. But so it's actually a adaptation of the implementation using Frederick gate. Okay? And here we see we use 3 fractional queries, 1/2 fraction queries. And we have this dagger operation, but this can be implemented probabilistically by this circuit. So by the way, we were just interested in implementing this probabilistically, but you can increase the success probability if you use more fine-grained time evolution like this. Okay. Now, again, so this implementation is different from the one considered by Araujo because first of all, it's probabilistic. The success probability is not 1, but it's non-zero for all input cases. And also, this requires multiple calls. Quite fun. Now, the question, okay, let's go back to the without fraction. So let's go back to the case without fraction queries. You only have a full query. In this case, so maybe the origins, so the naive controllization failed because you were too restricted on what you're asking for. Maybe if you relax your conditions, maybe something becomes possible. And then, so we actually took the fraction inquiry case where we allowed probabilistic implementation and multiple calls. And we consider this kind of quantum circuit and so whether we can actually implement this this function. Yeah, how much more time do I have? 2 minutes. Okay. Well, the message here is that even if you accept this part, you cannot implement it. How you show this is actually quite tedious because if you want to show something is impossible, you have to make sure that you go through, you treat all the possibilities, right? And this is actually quite technical. But so the first technicality is that let me go back one slide. Okay. First of all, in general, you should allow yourself a discarding ancilla, but if this can be implemented with discarding ancilla, you can implement it by measuring that ancilla. So you can forget about any discarding of ancilla. And then this whole circuit specified this red rectangle is actually a 4x4 matrix. Oh yeah, so I forgot to tell you one thing. We proved that first no rule for this particular unitary, which is the special class of SU2. Now, yeah, so we expel this U using this Pauli operators, and then so that this functional must be a function of theta. So if you express this functional in terms of theta and t, it must look like this. Then, so this function must equal to what we want. But if you compare the left-hand side, right-hand side, you can show this kind of equation, which means this. This means that if your input gate is Ix, right, then then this circuit cannot implement the controlled version of Ix. So this is a contradiction to our requirement. So what have we achieved? So we studied controllization gates with and without fraction inquiries. If we have fraction inquiry, we can implement what we call a weak form of controllization, where you allow probabilistic implementation and multiple calls. And if you also allow yourself inverse fraction inquiry, if you also have the power to implement inverse of fraction inquiry, then the success probability is at an arbitrary high. And finally, so if you don't have the fraction inquiry, even the weak controllization is impossible. And that's it.
Questions?
I have a question about how you're implementing the adjoint. The adjoint.
Adjoint. Oh, sure.
So it looks to me like that's linear in root U rather than conjugate linear.
This, right?
Yes.
This works because, first of all, did I mention? Okay, so this is possible because, so this is just one particular example that you can do this controllization. And to show that, I restrict myself to SU2. If it's SU2, the inverse can be implemented if you can take its complex conjugate and transpose, right? Well, I mean, any unitary is its inverse if you take its complex conjugate and transpose, right? So this middle part gives you this complex conjugate for SU2 by the point. Then this circuit actually gives you the transpose. Yes.
So they had a way to realize the controllization, and I understand the way you did, but I couldn't see a way to realize it in that paper. So
so they showed no-go result. Okay?
Yes.
So
this is the only thing I could see.
Yes. It's not their result that they showed how to circumvent the no-go. Okay. What I want to say more precisely is that in some cases, for example, if you consider in the linear optics where you have a vacuum where you implement the whole optical circuit with linear optical elements, then vacuum doesn't change, right? So in that case, that's all I'm saying.
I see. Thanks.
let's move on. Thanks again.
Thank you very much.